The ocean is the natural environment and field of operation for maritime nations the world over. It is logical and necessary that these nations learn as much as possible about oceans and their boundaries. The effective operation of naval forces is dependent upon this knowledge. Indeed, success or failure of specific naval missions can hinge critically on a commander's knowledge of a single environmental peculiarity of the water mass. Recognizing this, the Navy has given high priority to research and studies on problems basic to the science of oceanography. The U.S. Navy Electronics Laboratory, a leading bureau of ship's activity in oceanography, has had assigned to it several significant areas of oceanographic research. They are incorporated in the basic statement of the laboratory's mission. Thus, since 1946, basic oceanographic research has been an integral part of the program of the laboratory and has been vital to the support of various other programs of basic concern to the Navy. In pursuing its assigned task, NEL has acquired a number of special tools and facilities to expedite accomplishment of its continuing mission in oceanographic research. One of the first tools utilized by the laboratory was SCUBA. This apparatus permitted the scientist himself to enter the aquatic realm and make first-hand investigations in shallow water. For example, the diving biologist could intrude on the heretofore private life of various fish and aquatic invertebrates such as these Gorgonian corals. The use of SCUBA is highly rewarding, down to depths of 250 feet. Recognizing the significance of information to be gleaned from shallow water studies, but realizing the expense of operating seagoing vessels for this purpose, NEL devised and constructed a permanent oceanographic tower in 60 feet of water off Mission Beach, San Diego. This tower permits taking a wide variety of continuous measurements, which otherwise would require a vessel anchored in shallow water. Observations can be made 24 hours a day, month in and month out, with relative ease and economy. The bathyscaphe Trieste is another special scientific facility used by NEL. Following its acquisition in 1957 and arrival at San Diego, laboratory scientists initiated a program of seafloor and midwater investigations which utilized the deep diving capability of the bathyscaphe. This permitted in situ, or on the spot, observations and measurements by investigators in the fields of physical oceanography, seafloor geology, marine biology, and underwater acoustics. The Trieste is especially constructed to operate at very great depths. Indeed, it has penetrated the deepest known depth of the ocean. The logistics and cost factors of its operation make it less suitable for shallow water investigations than for deep ocean research. Another tool used by NEL oceanographers is the thermistor chain, mounted on the fantail of the USS Marysville. This sophisticated apparatus continuously traces temperature isotherms, that is, the depths through which given specific temperatures occur, and automatically plots them on a recorder. From these records, the movement of water masses and the dynamic thermal structure of the ocean can be interpreted. Records are verified by laboratory models, which in turn provide the basis for long-range theoretical studies. These tools and facilities, as well as others not covered here, have a varied application, and they all jointly contribute to the basic Navy requirement of advancing the knowledge of ocean environment and its several boundaries. Recently recognized is a distinct gap in observation capability between the lower operational depths of SCUBA and the economically practical upper depth of bathyscaphe operation. This gap is in the mid-depth area, generally considered to be between 200 and 6,000 feet. With the advent of the Cousteau SOUSCOUPE SOUS-MARINE, or submarine saucer, it was recognized that this type of underwater vehicle might fill the gap. Consequently, the Navy Electronics Laboratory made arrangements for use of this diving saucer when it became available for lease. NEL wanted to test its utility in several types of oceanographic research: physical oceanography, geology, biology, and associated disciplines. In a period of more than a year, over 21 dives have been made by 5 scientists from NEL. The purpose of this film is to document these dives and to present some of the results of the oceanographic investigations. Successful operation of the present Navy Electronics Laboratory Oceanographic Research Tower requires the best possible knowledge of the marine environment seaward of the tower site. Such basic surface, midwater, and bottom information is critical to the study of surface and internal waves which propagate from the deeper seaward direction. It is also critical to the success of acoustic tests being made in the area in close conjunction with the tower research program. It was quickly realized that the diving saucer provided an excellent means for gaining much of this information. Therefore, one of the early dives of the saucer was made by physical oceanographer Eugene C. Lafon. The saucer submerged immediately seaward from the tower and proceeded westerly toward deeper water. There were 2 objectives. First, to extend geographically the environmental inventory of various physical, geological, and biological features which exist around the tower. And secondly, to gain information for the installation of future structures to be used in conjunction with the present tower. Immediate scientific targets were the distribution of water temperature, turbidity, and bottom currents, and visual sampling of bottom microtopography, geologic features, and benthonic faunal populations. The dive was closely coordinated with a series of measurements taken simultaneously from the tower. Current at the bottom was only 1/10 of a knot to the south, but winter swell had created large sand ripples 30 inches across and 6 inches high. These ripples were scalloped and irregularly eroded with furrows along their crests. This was caused by the burrowing action of sand dollars, which would alternately crawl and then partially bury themselves in an erect position. The partial burial was always in an orientation giving least resistance to bottom currents. Farther seaward, the ripples became smaller, and the sand dollar population ended. Also, the ripples became sharp-crested. As the SOUSCOUPE proceeded farther, a layer of broken shell was seen to make a hard white band in the troughs. Still farther, the ripples became smaller. Finally, they disappeared as a flat, silty sea bottom, characterized by sea pens, was traversed. It was also noted that both bottom current and turbidity increased as the saucer moved progressively farther from the tower. The saucer was submerged for nearly 4 hours on this dive and covered a controlled track of about 2 miles. Results clearly delineated the contrasting zones seaward of the tower, with characteristic relationships between bottom roughness and bottom-dwelling populations. These relationships help clarify certain anomalies in sound reflection from the sea floor in this area. The dive further established the feasibility of constructing other bottom-mounted installations in deeper water, as no large rock outcrops, unstable bottom conditions, gullies, or other natural obstructions were encountered. Some 60 nautical miles north of San Diego, off the coastal town of San Clemente, marine geologists from NEL have been investigating unusual geologic seafloor features for many years. Since 1959, offshore explorations have been made with precise electronic position control. Use is made of shore-based beacon stations which respond to electronic commands from the ship. The results are electronically and mechanically plotted on a chart of the area. This permits the ship to know its location exactly and to reoccupy positions previously studied. In some of his earlier work, marine geologist Edwin Buffington developed theories about the origin of gullies on the sea floor and about the stability of sea floor slopes. Effort was concentrated on the gullies because they provided a localized site for geological events which control the distribution of sediment. This is especially important in predicting sedimentary conditions in the deep sea and their effect on long-range sound transmission. The diving saucer provided an exceptional opportunity to examine firsthand the features and processes which had been interpreted from echo-sounding records and samples. Proceeding to a spot especially chosen from previous records and located with the navigation system, the geologist selected a dive site. The bottom was checked with the echo sounder and the descent position buoyed. Scientist and pilot carefully planned the dive. In the first dive, the saucer descends the wall of one of the sea gullies and checks for rock outcrops which are expected from the seismic profiling records. Large outcrops are not found, but the slopes are discovered to be greater than 40 degrees, which is more than twice as steep as those measured by echo sounder. A sample of the sea floor is taken by extending the saucer's hydraulic arm with an attached core sampler and tilting the saucer until the core penetrates the sea floor and brings out a sample of the sediments. Rock outcrops are found at considerably greater depth than expected. At near maximum depth of 1,000 feet, slumps and landslides are found. Vertical cliffs are encountered next to slopes of unconsolidated sediment which are as steep as 45 degrees. Apparently, very steep slopes can be quite stable and still be close to slopes which are unstable. A bonus observation of interest to both biologists and geologists is made when swarms of squid are seen to have a habit of striking the bottom as they feed, creating large clouds of turbid sediment close to the sea floor. This biological action accomplishes a redistribution of sediment and a smoothing of the bottom, with a consequent change in the nature of the reflecting bottom surface. The dives at San Clemente corroborated the conclusion of original studies which bore on the origin of the gullies and their relations to slumping and slope failure. The observations also gave considerable encouragement to the observers for continuing work and seafloor observations in this area with the promise of finding more productive information. For the past several years, marine geologist David G. Moore has been directing a series of investigations utilizing continuous seismic reflection profiling systems. This work has been conducted from shipboard and has covered large segments of the continental borderland off Southern California, in addition to areas from the Mediterranean to the Asiatic coast. In his studies, the acoustic characteristics of sediments and rocks, which produce reflection of sound waves, were the key element. For this investigator, the diving saucer provided a new opportunity to study and sample those areas of the sea floor where sub-bottom strata, which give reflections, emerge to the surface. Resulting information allows more realistic interpretation of the geophysical records, in which the true nature of buried rock can be extended as long as the seismic reflections can be identified. Moore made dives in two locations. The first was on Coronado Bank near the Mexican border, where a prominent submarine canyon incises the edge of the continental shelf. Here he found and sampled sediment which provided the basis for identifying several seismic reflecting layers. These identifications provided useful clues to the basic geologic nature of the bank, the processes responsible for producing the canyon, and the relation of the bank to the fundamental structure of the borderland. The second location was off 30 Mile Bank to the west of San Diego, where the sea floor shoals to within 800 feet of the surface. Here, spectacular outcrops of ancient lavas were found, bearing mute testimony to volcanic activity in the geologic past. 100-foot-high exposures of this basalt, covered with sponges and other types of sea growth, were observed. This type of rock had been found by dredging carried out in previous years, but the exact nature of the exposures and their relationships to adjacent sedimentary rocks could not be known until actually viewed and explored by the diving saucer. The ability to inspect these exposures virtually at arm's length provides insight into the seafloor processes of weathering and chemical erosion. The additional contributions to erosion made by various rock-destroying animals moving about at will demonstrated another facet of the entire erosional process. Observations on the activities of such animals at these depths are essentially impossible without a submersible. The understanding of the chemical and bulk physical properties of sediments and characteristics critical to the absorption and reflection of sound takes a significant step forward each time a contributing process is revealed. One of the early observers of the seafloor by direct visual methods is marine geologist Robert F. Dill. Starting in 1950, this scientist has concentrated his effort on in situ measurements of the mass physical properties of the marine sediments and sediment movement down submarine canyons into the deep sea. Much of his work was done with scuba, which limited observations to depths above 250 feet. The arrival of the saucer, therefore, was especially welcome to Dill, for it permitted him to extend his observations to 1,000 feet. His saucer investigations were conducted off Southern California, where the canyons cut through sedimentary rock, and in Mexico, where they cut granite. Studies in these diverse environments were undertaken to determine whether the responsible erosional processes were unique to one rock type and locality, or whether they could be applied to most submarine canyons. The dives in San Lucas Canyon, Mexico, extended observations from the previously studied Sand Falls depths down to the main axis of the canyon. In the tributaries, sandy fill periodically flows down slope, eroding the granite walls and transporting large amounts of wall rock. Saucer observations showed that below the sandfall area, in 950 feet of water, angular blocks of freshly broken granite, as large as 10 feet, rested on or were partially buried in the sand fill. Large ripple marks and scour depressions below the sandfall area indicated that the bottom had been subjected to currents of up to half a knot. Recent instability was also suggested by these cobbles, carried down canyon by progressive slumps to a depth of 1,000 feet. In the main channel above those depths where the tributaries spill sand into the canyon, sediment was found to be highly reworked by marine organisms and to be accumulating at a rate of approximately 2 inches per year. These observations contradict a common belief that submarine processes become more inactive as depth increases. Also of significance to Dill were the bare rock surfaces found only at the base of vertical and overhanging walls. The living population which existed a short distance above the eroded areas constituted evidence of recent erosion. Grooves, gouges, and striations on the rock walls further indicated that the sediment fill of the canyon was slowly moving down slope and had sufficient internal strength to grind away the wall rock. The saucer dives indicated that the primary transporting and eroding processes in canyon depths to 1,000 feet were slow gravity creep, progressive slumping, strong bottom currents, and sand flows in steep areas. The basic agents contributing to erosion of the canyon walls were found to be similar in both sedimentary and granitic rock environments, thus establishing geological processes of considerable significance. Knowledge of these processes provides another element in permitting prediction of the ultimate resting place and distribution of shallow water sediment in the deep sea. Since first discovered at the beginning of World War II, oceanographers have been puzzled by the presence, on echo-sounding records, of a midwater sound-reflecting layer. It was noted that this layer, termed the deep scattering layer, descends at dawn from its nighttime roost near the surface and rises at sunset. Thus, it was suspected to be of biological origin. Also of considerable interest were the strong, discrete reflectors called tent fish, because of their signature on the echogram. The cause of this scattering layer has been the scientific target of marine biologist Eric G. Barham. His early investigations included attempts to sample the layer by dragging nets through it to catch organisms. Although various animals were retrieved, it was never certain that a true sample was obtained, since it was always possible that some of the reflecting organisms were fish which could elude the net. Clearly, the best way to study this layer was to actually get into it, stay in it, and observe. Although the deep scattering layer had been penetrated by the bathyscaphe Trieste en route to the bottom, investigation of this area was made to order for the diving saucer because of the saucer's excellent maneuverability and capacity for hovering at a controlled depth over a long period of time, something the Trieste could not easily do. Barham's dives in the SOUSCOUPE were made in mid-water off Cape San Lucas. They were carefully scheduled to cover the time when the scattering layer began its upward migration at dusk and its descent before dawn. Thus, dives were started in the late afternoon and continued into the hours of darkness, with the ascent and recovery of the saucer made at night. The dive plans required that the SOUSCOUPE descend to a given depth and hover for an extended period, maintaining controlled depth to within 5 meters. It was to turn off its lights, remain as motionless as possible, and then illuminate the area and photograph the creatures before they were affected by the light. Simultaneously, records were taken by a surface ship to indicate acoustically the position of the saucer with respect to the scattering layer. This technique proved to be highly successful, and enough animals were identified to give considerable confidence to previous speculations on the composition of the layer. Small fish, known as myctophids, sometimes called lanternfish, were the main component. In addition, squid were observed feeding on the lanternfish. A second component of the scattering layer was found to be Physonect siphonophores, similar to this large jellyfish-like colony. In addition to information on the scattering layer, a considerable amount of data was gathered concerning the nature of strong, discrete reflectors of biological origin, but which give signatures that could be confused with foreign objects invading the environment. An interesting incidental observation during these dives was the discovery of a possible new form of flounder, temporarily named Sally Rand, for obvious reasons. The dive series ended in April 1965. It was the unqualified opinion of all scientific observers that the series was a distinct success. It was also concluded that mid-depth submersibles were extremely useful in making physical, oceanographic, geologic, and biologic investigations. In addition to the 21 dives made by NEL oceanographers, investigations were made with Navy Electronics Lab installed equipment during dives when an NEL scientist could not be the observer. Underwater electromagnetic propagation was investigated in this manner. When operating in foreign waters, the laboratory extended the courtesy of participation in the diving program to foreign scientists. the director of the Geological Institute of Mexico at the University of Mexico, Dr. Guillermo T. Solis, made a dive off Cape San Lucas, which was especially interesting and profitable. Cooperative use was made of the observations and the gathered data. New research mid-depth submersibles with extended capability in submergence time, distance, and speed are continually being developed. New equipment and systems to take advantage of these capabilities are being planned for a future assault on scientific problems which could not even be considered a few years ago. Scientists of the Marine Environment Division of the Navy Electronics Laboratory anticipate greater accomplishments as the depth barriers for underwater observations are steadily pushed back. Routine examination of the sea floor and of the ocean mid-depths will then become a reality rather than just a dream.